We present a late-breaking work on modeling reciprocal adaptation in HCI with a multi-agent reinforcement learning approach. This is Tanay Gupta from BITS Peladi and Julien Gori from UCLS. Designing and evaluating adaptive systems is difficult because of the long-term reciprocal adaptation between users and the adaptive systems. In this work, we make the hypothesis that the design of adaptive systems can be bootstrapped by using synthetic user models that are able to adapt. We also view interaction from a multi-agent perspective, being formed by three components: a passive task, a user agent which interacts with the task, and an assistive agent which is capable of actions which affect the interface. To determine user and assistant behavior, we build on multi-agent reinforcement learning. In this paradigm, the user and assistant agents select actions according to a so-called policy. The joint actions are forwarded to the task, which transitions from a state to another according to some probability model. Upon transitioning, the task issues rewards to both agents, which then produce an observation of the new task state, and the cycle continues. The goal of MARL is to find the policies for both agents that maximize their rewards. We now introduce the task that we chose to study and how it can be translated as a MARL problem. We consider a grid wall type task with dummy targets in black, a target to be reached in red, and a cursor in green. The user can indicate whether it wants to go up, down, left, or right, and the assistant can choose a gain of 1, 2, 3, or 4. For example, if the user selects down and the assistant selects 3, the cursor will move 3 units down. While the user can see everything, the assistant cannot see the target. However, the assistant has memory and can exploit that. Both agents get equal rewards. We devised an algorithm that is a variation of a multi-agent actor critic algorithm by Lowe and colleagues, which has one critic and one actor per agent. In our case, because the goals are aligned, we actually use a single critic. We use the decentralized training, decentralized execution approach, where all information is available during training, but not execution for the assistant. We also randomize grid layouts and vary the amount of dummy targets, and to help the agents learn, we use some form of curriculum learning. Now, we first note that the agents were able to learn. The pair was 30% more efficient than the optimal unassisted user. We then investigated the effect of memory for the assistant, and we showed that memory is in fact important for performance, likely because past observations may be used to infer the target. In this particular task, the two last user actions were the most important. We also performed an ablation study to show that the assistant was able to exploit the grid information. And finally, we also show that the assistant tends to undershoot the target, compared with the optimal policy where the true target actually known. Now, to summarize, we presented a proof of concept for MARL in HCI. A lot of work remains to be done. The first direction is to increase the scale of the task, mainly by using continuous action spaces for both agents. It would also be interesting to evaluate obtained policies, be it user or assistant policies, and compare them to real and existing ones.